Example 2. A study asked whether college students could tell dog food apart from expensive liver pâtés, liverwurst, and Spam. God, I don't even know what liverwurst is. All were blended to the same consistency, chilled, and garnished with herbs and a lemon wedge, just to make it look pretty. Students were asked to identify which was dog food. Researchers wanted to test a probability model where the students are randomly guessing. How would they test their hypothesized model? Okay, so see the download that shows how many students picked that item to be dog food. So it seems that college students have a bunch of different choices. They have dog food, liver pâtés, liverwurst, and Spam, right? And then they need to identify which was dog food. So out of those, which of those is dog food? So sort of like a multiple choice question. So if you hit example 2 in the download that's listed below, you'll see the number of students that selected that particular item as dog food. Now, be careful because some people right here, remember, you might get this problem on a test and you won't know that it's a chi-square problem. Sometimes people might immediately just think, I'll find the mean, right? And so they just go ahead and find the mean. But then if you do find the mean, ask yourself, what does this mean, right? What is the idea or the concept? If we average this, we would find the average number of students that selected any of these items as dog food. And that's sort of a mean that doesn't make any sense, right? And so before you go ahead and find the mean, ask yourself whether the mean is actually meaningful, right? So here, we know that it's a chi-square because the students are choosing something, and it's a categorical choice. They're not giving you an answer like 20 inches or 50 degrees or I got 10 questions correct, right? They're actually just saying that one is dog food, right? And they have 5 different choices, and they've chosen one of them as dog food. So out of 5 choices, a probability model that they're just guessing would mean that 20% of the time they should pick pâté 1 to be dog food, 20% of the time they'll pick Spam to be dog food, 20% of the time they'll pick dog food to be dog food, and so on and so forth, right? So let's draw that probability model. And by model, we often mean null hypothesis, right? Model or hypothesized population. So step 1. So the null hypothesis is the idea that they will fit into this picture. So if this is the population, right, and it's out of 100%, and they have 5 choices. Oh, my picture is just slightly uneven. It helps to really draw this as well as you can, just because then it'll help you reason too. That they'll have an equal chance of guessing either one of these. And there's 2 liver pâtés. That's why there's 5 choices, right? So liver pâté 1, so liver pâté 1, I think Spam was next, and then actual dog food, just in the data set. What was I forget. Oh, pâté 2, and then liverwurst. So I'll say pâté 2, and then liverwurst. All right, so these are the 5 choices. And we're saying, look, the students are just guessing. They should have a 20% probability of each. Is this the right proportions for this sample? Is the sample going to sort of match this or be very different from this? The alternative is that at least one of the real proportions is different from predicted. Okay, so once we have that, we could set our alpha to be 0.05. Our decision stage, we could draw a chi-square, right? And our degrees of freedom, we now have 5 categories, And so our degrees of freedom is 5 minus 1, which equals 4. And it's because once we know 4 of these, right, then we could actually figure out the proportion for the fifth one just from knowing 4 of these. So that one is no longer free to vary. It doesn't have freedom anymore. It's sort of locked in. Okay, so what is our critical chi-square? Well, if you want to pull up your Excel data, here I'm just going to start off with step 3. In step 3, our critical chi-square, in order to find that, we could use chi-inv, put in the probability that we're interested in, and our degrees of freedom, which is 4. And so our critical chi-square is 9.449. 9.49. Notice that as degrees of freedom goes up, right? As degrees of freedom goes up, what's happening to the critical chi, what's happening to the chi distribution is that it's getting fatter. It's getting more variable. And because of that, we need a more extreme chi-square value. So that's sort of different than like T distributions or F distributions. There, those distributions got sharper when we increased our degrees of freedom. Chi distributions work the opposite way. Those chi distributions are getting more variable as degrees of freedom goes up. Okay. So once we have this, now we could start working on our actual data, our actual sample. So step 4 is we need to find the sample's chi-square. And in order to do that, it helps to draw out that table. So the table might look something like this. I'll just copy this down here. Right? And this is the type of food. Right? So that's the category, right? And here we have our observed frequencies, the actual number of students that pick that thing to be dog food. So here we see 1 student picked pate 1 to be dog food. 15 students picked liverwurst to be the dog food. What are the expected frequencies? Well, in order to find expected frequencies, we know that the expected proportions are going to be 0.2 all the way down, right? 20%, 20%, 20%, 20%, right? And here, I'm just going to total these up. Sum, total, same thing. And I see that 34 students were asked this question. Our expected frequencies should add up to about 34. Our expected proportions add up to 1, right? And that's why we can't just directly compare these two things yet. They're not in the same sort of currency yet. You sort of have to change this currency into frequencies. So how do we do that? Well, we imagine here are all 34 students. Take 20% of them. How many students will that be? So that's 0.2 times 34. This times 34. And I'm just going to lock down that 34 because that total proportion, sum won't change. So this is what we should expect. That's if they were indeed guessing. This is the expected frequencies that we should see. And if I just move that over here, we'll see that that column also adds up to 34. Now, once we have that, we can compute our actual chi-square. Because remember, that's observed frequency minus expected squared divided by expected as a proportion of expected. So that's the observed frequency minus expected frequency squared divided by the expected frequency. And I could take that down for each row and then add those up. And here I get my chi-square statistic for my sample. And so my sample chi-square is going to be, I'm just going to put a pointer right here, is 16.29. And that's a larger, more extreme chi-square than my critical chi-square, right? And so let's also find p-value here. In order to find p-value, I could use chi dist. Here I put in my chi-square and my degrees of freedom, which is 4. And so that's 0.003, and that is certainly smaller than 0.05. And so in step 5, we reject the null. Now I just want to make a comment here. Notice that here, after we do the chi-square, although we reject the null, just like in the ANOVA, we don't actually know which of the categories is the one that's really off. When we eyeball this one here, we could sort of see this one probably seems to be the most off, but we're just eyeballing it. We're not using actual statistical principles. So once you reject the null, there's post hoc tests that you could do, but we're not going to cover those here. All right, so it seems that students are not randomly guessing. They actually have a preference for something as being dog food. My guess is liverwurst. I don't even know what that is. Okay, so example 3. Which of these statements describe properties of the chi-square goodness of fit test? Okay, so if you switch the order of categories, the value of the test statistics does not change. That's actually true. It doesn't matter whether candidate A got added before candidate B. Addition is totally order insensitive. You could add A then B or B then A. You could add pate then liverwurst then dog food, or dog food then liverwurst then pate. Sort of doesn't matter, right? So this is actually true. That's a true property. Observed frequencies are always whole numbers. That's also actually true, because when you observe the frequency, you're actually counting how many category members you have. So counting is going to be made up of whole numbers. Expected frequencies are always whole numbers. That is actually not true. Expected frequencies are predicted frequencies. It's not that at any one time you'll have 6.8 students saying that liverwurst is dog food, but it's that on average, that's what you would predict given a certain proportion, right? And so this is actually not true. Expected frequencies don't have to be whole numbers because they're theoretical. They're not actually things that we counted up in real life. A high value of I almost said x squared, of chi-squared indicates high level of agreement between observed frequencies and the expected frequencies. Actually, if you think about the chi-square statistic, this is actually the opposite of what is actually the real case. If we had a high level of agreement, this number would be very small. And because this numerator is small, the chi-square would also be small. A high value of chi-square would actually mean that this is quite large compared to this, right? And so this is actually also wrong. It's the opposite.